Alright, in this video we're going to be talking about the laws of exponents. Those are the rules that we can use to work with and simplify expressions that involve exponents. Alright, so what I have here is a few examples involving just numbers and variables that we will work our way through and then simplify them and then use those to figure out, well, what is the general law for something that has that form? Alright, so the first one we have here, 5 to the third power times 5 to the first power. Alright, so what does that look like? Well, 5 to the third power, if I expand that, that's 3 5s multiplied together, right? 5 times 5 times 5, that's 5 to the third power. But then that's multiplied by 5 to the first power. So multiplied by another 5, just one 5 this time, because 5 to the first power is just one single 5. Right, so I have 3 5s multiplied by one more 5. So how many 5s do I have in total multiplied together there? Well, I have 1, 2, 3, 4. Right, so 5 to the third times 5 to the first equals 5 to the fourth power. Right, because when I expand this, I have 3 5s multiplied by one more 5. That's 4 5s multiplied together. That's by definition 5 raised to the fourth power. Right, so when I am multiplying two things that have the same base, right, they both have a base of 5, what I do with the exponents 3 and 1, I don't actually multiply the exponents there. A lot of people make the mistake of saying, well, since I'm multiplying, I need to multiply the exponents, and 3 times 1 gives me 3, so it should be 5 to the third power. But as we can see, it's not 5 to the third power, right? We actually have 4 5s multiplied together as 5 to the fourth power. So when you are multiplying these two things with the same base, you have to add the exponents together to get the final result. So a to the m times a to the n equals a to the m plus n power. All right. So when you have, again, the same base being multiplied together, you keep that base the same, right? Notice we don't actually multiply the 5s here. It doesn't become a 25 raised to a power, right? It stays as a 5, and then I just take the exponents 3 plus 1 and get the fourth power. Right? So anything in that form, a to the m times a to the n equals a to the m plus n. I'll write this hopefully a little more clearly so you can see it. Right? So when you're multiplying with the same base, you add the exponents, you keep the base the same. All right, the next one, 6 to the 7th power divided by 6 to the 4th power. Right? So here we are dividing two quantities. They both have the same base, but they're being raised to different exponents. So let's see what happens when we expand this one. If I have 6 to the 7th power, that means 7 6s multiplied together. So 1, 2, 3, 4, 5. I should have picked a smaller number there. So that's 7 6s multiplied together. And then in the denominator, we have 6 to the 4th power. So that's 4 6s. 1, 2, 3, 4. All right. And then as we saw when we looked at that video on fractions, all right, when we have the same factors in the numerator and denominator, each one of these 6s in the numerator can cancel out one of the 6s in the denominator. Right, so I can cancel out basically 4 of those 6s in the numerator, right? Because I have those 4 in the denominator to cancel those out, and I'm left with 3 6s in the numerator. So I end up with a 6 to the third power. Right, so 6 to the 7th power divided by 6 to the 4th power actually leaves me with 6 to the third power. Right? These 4 6s here cancel out 4 of the 6s up above, and I'm left with just 3 6s left behind. Right? So when I am dividing these things and they have the same base, I don't divide the exponents. I don't do 7 divided by 4. I actually subtract those two exponents. Right? If I do 7 minus 4, that gives me the exponent of 3. Right? Which, as we see, the reason we subtract those is because these 4 that we have down here, when I cancel those out from the numerator, I'm subtracting those 6s away and leaving only 3 behind. Right? So the general rule, a to the m over a to the n, right? When I have the same base and I'm dividing, I keep that base the same and I subtract the exponents. It's a to the m minus n power. All right, so those are the first two rules of exponents, and these two come up a lot. And this stuff is actually things that a lot of math teachers in high schools and colleges complain about, that students just don't know the rules of exponents very well. That's why I'm trying to show it to you this way, and we'll do this for these other examples up here as well. Show it to you how the rule comes about, why it is what it is, rather than just memorizing a whole bunch of rules. If you just try to memorize a whole bunch of rules, they're really easy to get mixed up or to forget exactly what they are. But if you understand that when I'm multiplying, this is what actually happens, and I actually have to add all those together to get the new exponent, or when I'm dividing, I'm actually canceling things out, and that's why I have to subtract. If you understand where that comes from, it makes it a little bit easier to remember what the actual rule is. Like I said, rather than just memorizing a whole bunch of rules. All right, so for the next one here, 4 to the third power, and then that in parentheses raised to the second power. All right, so what do I have here? Well, I have 4 to the third power, which means I have 3 4s multiplied together, right? So that's 4 to the third power, but then that's being raised to the second power, which means I have 2 of those. Right, so I have 4 times 4 times 4 times another 4 times 4 times 4, right? There's 2 exponents here, so this one's a little bit trickier, right? The 4 to the third power inside the parentheses, that's three 4s multiplied together, right? But then that entire set, I have 2 times, because I have the exponent of 2 outside of the parentheses, so I have that entire set 2 times, so I have 2 sets of those 4s multiplied together, right? So how many 4s do I actually have here? Well, I actually have 6 4s being multiplied together. This is 4 raised to the 6th power. All right. So I hope that one makes sense as far as how we get that. Maybe a better way to look at it, maybe like an intermediate step here, is I have 4 to the third power squared, which means I have a 4 to the third multiplied by another 4 to the third power. Right? Just taking whatever's inside that parentheses to the second power means I take that parentheses and multiply it by itself, twice. And then each of those 4 to the third powers is the 3 4s multiplied together, which gives me a total of 6 4s. So maybe throwing that extra step in there helps it make a little bit more sense to you. But what we get here when we have a power raised to a power is we actually have 3 times 2 equals 6, right? So when we have a power raised to a power, we actually multiply those 2 exponents together. So if I have a to the m to the nth power, that equals a to the m times n. Right, a power to a power you multiply. And the reason you multiply is because, well, I'm taking this whole parentheses twice, but then in that parentheses I have 3 more, and so I multiply 3 times 2 to get that total number of 6 that I ended up with here. All right, so a power to a power you have to multiply. All right, the next one, 2x in parentheses raised to the third power. Right, so once again we have a parentheses raised to a power, but it's not the same as what we had up here. Right, up here we had inside the parentheses was something to a power. Here inside the parentheses we have multiplication, right? 2 times x, and then that whole quantity raised to the third power. All right, so let's see what we get if we expand this. All right, so we would have 2x multiplied by itself 3 times. All right, because whatever's in this parentheses being raised to the third power means whatever's in that parentheses I multiply 3 times. So it's 2x times 2x times 2x. And now if I combine this stuff together, well, if I do 2 times 2 times 2, that's a 2 to the third power. If I do x times x times x, that's an x to the third power. Right, so 2x in parentheses raised to the third power is equal to 2 to the third power times x to the third power. Right, so when you have multiplication within a parentheses and a power on the outside, basically what you can do is you can distribute that exponent to the stuff that's inside the parentheses. Right, so if I have a times b in parentheses raised to the nth power, that gives me a to the nth power, b to the nth power. Right, so again, if I have multiplication inside the parentheses, I can distribute the exponent to all the things that are inside there. Right, same thing for division, as we'll see in this next example. If I have x divided by 3 raised to the 4th power, well, that means I take that x over 3 and I multiply it by itself 4 times. So x over 3 times x over 3 times x over 3 times x over 3. Right, so the 4th power means I take whatever's in that parentheses 4 times, multiply it all together. Now if I multiply this out, I multiply x times x times x times x. That's an x to the 4th power. And 3 times 3 times 3 times 3 in my denominators, that's a 3 to the 4th power. Right, so just like with the multiplication up here, when I have division inside the parentheses raised to a power, I can distribute that exponent and just make it x to the 4th over 3 to the 4th. And that gives me like a little shortcut to actually doing all this work that I just did up here to write it all out. Right, so the general rule, if I have a over b raised to the nth power, that's going to give me a to the nth over b to the nth power. All right, so when I have multiplication or division within a set of parentheses and that parentheses is being raised to a power, it's almost like the distributive property. I just take that exponent and I distribute it to all the things that are inside there. Right, notice we don't have a law up here for, like, if it was 2 plus x raised to the 3rd power, that's not 2 to the 3rd power plus x to the 3rd power. All right, just to give you a little side example here, right, if I have 2 plus x to the 3rd power, right, that's not 2 to the 3rd plus x to the 3rd. When there's addition or subtraction in the parentheses, I don't just distribute the exponent. Right, so remember, 2 plus x to the 3rd power, what that would actually equal would be 2 plus x times 2 plus x times another 2 plus x, and then I have to use the rules for multiplying these things together, and it's going to give me something that's a bit more complicated than just 2 to the third power plus x to the third power, right? And that's something we'll get to in another video of how to deal with something in parentheses with addition or subtraction raised to a power, right? But these are 3, 4, 5 of the basic laws of exponents, really important to know. And again, I showed them to you this way, and hopefully, seeing it all written out and like expanded and then simplified helps you understand why the rules are what they are. If you know why they are, it makes it easier to actually remember what they are. All right, so I'm going to pause the recording here, and then I'll put up some more stuff that have to do with negative and zero exponents, which there's different rules for those as well. All right, here we're going to look at now negative exponents and zero exponents and see what the rules for those are and why the rules are what they are. All right, so what I have here is just a list of the powers of 2, and this works for really any base. I chose 2 just because it's small numbers and it's easy to work with, but you can do the same activity here with powers of 3, 4, 5, or whatever other number you want. All right, so we have the powers of 2 from 2 to the 4th power, counting down to 2 to the negative 4th power. We're going to use the pattern to figure out what those are actually equal to the rest of the way down. I filled in the ones for the positive exponents. We'll figure it out for the zero and the negative exponents. And then we're going to write those ones with a negative exponent with a positive exponent and try to use that to figure out what the rule is. Right, so 2 to the 4th power, that equals 16. If I multiply 2 times 2 times 2 times 2 4 times, I get 16. 2 to the 3rd power equals 8. 2 times 2 times 2 is 8. 2 to the 2nd power is 4, right? That's just 2 times 2. 2 to the 1st power is just 2, right? Remember, anything to the 1st power is just the base number itself, right? So if I use the pattern here to figure out what 2 to the 0 power is. So what is the pattern? To go from 16 to 8 to 4 to 2, what do I have to do each time to get from one number to the next? Well, for each one, I would have to divide by 2, right? 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is going to give me 1, right? So 2 to the 0 power equals 1. All right, what about for the next one? What's 1 divided by 2? That's going to be 1/2, right? So 2 to the negative 1 power is 1/2. For the next one, for 2 to the negative 2 power, well, I just keep continuing the pattern. 1/2 divided by 2 is going to give me 1/4. If I do 1/4 divided by 2, that's going to give me 1/8, and 1/8 divided by 2 is going to give me 1/16, and that's the value of 2 to the negative 4th power. All right, so we see what we get here when we use the pattern. Again, for the powers of 2, I divide by 2 each time to kind of work my way down to get the next one. So if I had a base of 3 here, well, then I would be dividing by 3 each time to get the next number. And if you want to try that on your own just to see what this would look like if you use a different base, it's the same idea, it's just you're dividing by a different number each time. Basically, you're dividing by the base number. All right, so we see here that 2 to the 0 power equals 1. 2 to the negative 1 power equals 1/2. How do I write that with a positive exponent? Well, 1/2 is 1 over 2 to the 1st power. Right? 2 to the negative 2 power is 1/4. Well, 4 is 2 squared, so 1/4 is 1 over 2 to the 2nd power. Right? 2 to the negative 3 is 1/8. Well, 8 is 2 to the 3rd power. So that's 1 over 2 to the 3rd power. So notice, the numbers I have up here for the positive exponents, basically I get the reciprocal of those numbers down here with the negative exponents, right? The 2 and the 1/2, the 4 and the 1/4, the 8 and the 1/8, the 16 and the 1/16. And if I had 2 to the 5th power and 2 to the negative 5th power, those would also be reciprocals of each other. Right? So 2 to the negative 4th power, that's 1 over 16. Well, that's 1 over 2 to the 4th power. All right? As we see up here, 2 to the 4th power is 16. Right? So that's what we end up with, right? When we have negative exponents, we actually end up with the reciprocals of that same base raised to a positive exponent, right? So that leads us to our rules for 0 and negative exponents, right? Anything raised to the 0 power, right? Like 2 to the 0 power here was equal to 1. Whatever that base is, it's going to equal 1 when I raise it to the 0 power. 2 to the 0 power, 5 to the 0 power, 1,032,000 to the 0 power, they all equal 1, right? And a to the negative n power, right? Anytime I raise something to a negative exponent, as we see with these over here, I get the reciprocal of that same base raised to the positive exponent. All right, so a to the negative nth power equals 1 over a to the positive nth power. Right, so those are our rules for 0 exponents and negative exponents, right? And add those on to the ones we had up here before with all the other laws of exponents. Those are the things you need to know about exponents moving forward and doing algebra, precalculus, and calculus.